In this video, I will provide an introduction to mobile networks and services, which is also the name of a course at the KTH Royal Institute of Technology in Sweden. And I will particularly talk about the basic wireless communication and how it has evolved over time and how some of the most important features of it is operating. So this is all about communication. And what is communication? Well, that is the information transfer between two different points, potentially at different times as well. So if you look back in time, classical ways of doing communication was to write information in newspapers or in books and transfer them to other people, or to use the telegraph to send information over distances, or radio, TV, broadcasting. But today, when we are talking about communications, it's more modern technologies that people have in mind. Might be CD, DVD, or Blu-ray discs, or USB memories that we are transferring information using, or optical fibers or network cables, or the different wireless technologies like 4G, 5G, or Wi-Fi. So this is, of course, an illustration of how our base station in a mobile network is sending information back and forth to a mobile phone. And this is a technology that is evolving very rapidly. So what I'm showing here is different technologies, wired technologies and wireless technologies, and how they are evolving in time. And in particular, I'm showing different data speeds or bit rates that we can deliver. And notice that there is a linear time scale here on the horizontal axis, while there is an exponential, so 10 times increase here along the vertical axis. And what we can see is that over time, we are developing new technologies that are making sure that the bit rates are increasing very rapidly, both in the wired and in the wireless scenarios. And here we are going up to different 4G technologies. And since we are seeing this increase here, there are new research challenges and new reasons to learn how to develop new technologies that are continuing to push these bit rates upwards over time. And there is something called the Martin-Cooper law that says that the number of voice and data connections has doubled in the world every 2.5 years, meaning that 32% increase in the total traffic in wireless technologies or in wired technologies. You can see here as well, there's typically 10 times difference here. So all of these type of things are increasing all the time. So even if you think that today we have a technology that works good enough, well, we need to improve it in the future just to keep up with this increasing use of technology. Here's another way of looking at that fast traffic growth. So this is data from the Ericsson Mobility Report, which is showing the number of exabyte per month that is sent over different wireless technologies. 2G, 3G, 4G, that is the yellow bars here, and then adding 5G over time is the orange bars. And what we can see here, according to their predictions, over the next few years, we will see a traffic growth of like 45% per year, which is even faster than the Martin-Cooper law from the past. And it shows that we are sort of increasing the amount of data traffic in our networks with 42 times over 10 years. And this is created by a number of different things. One is the number of subscriptions. So if we are looking at the number of subscriptions in the world for different wireless technologies, where they are increasing over time, but not with this pace. So it's both that we are using more devices that are connected wirelessly, but particularly that the devices that we are having are also used more and more. And you can see all of these different types of connectivity here, that eventually 5G will be having a big piece of this pie, but there's also 4G and 3G and other technologies that are contributing to the number of total mobile subscriptions in the world. So what has then been the impact of this fast traffic growth, the use of wireless connectivity in our world? Well, first of all, it sort of shrinks the world together in a way that people can be anywhere and still be connected to each other. And people are also nowadays always connected around the world. So it's really also the thing that we can't really live our lives without being constantly connected and getting information wirelessly to our different devices. And this has really profoundly changed the way that people are communicating with each other. So it started with the mobile phone in the 80s and 90s with the fact that all of a sudden you're not calling or contacting a physical place anymore. So like sending a letter or making a phone call to a landline to one particular telephone, but you're reaching a person, so you know who you're contacting. But nowadays also with all the kinds of social networks that are the ways that people are primarily communicating with each other, that is powered by wireless connectivity. And we have also seen sort of a convergence of the wireless networks into having fewer and fewer standards that are carrying more and more data traffic. And looking a bit further into the future, well, we would say that now 5G that has recently been deployed sort of supposed to be an enabler for the digitalization of society. So we are talking a lot about smart cities, smart homes, Industry 4.0, and other developments where things will be connected and we will benefit from that in order to make things more efficient in our world. And of course, the wireless technology is the backbone of that development. Without the connectivity, we will not be able to provide any of these other services. So as a person, probably the next consumer service that we will be discovering is augmented reality. People like me here, we will be walking around with some kind of augmented reality glasses that is mixing our physical world with the digital world, and that will be sort of a revolution just in the same way as a smartphone is going to be. And in order to deliver that kind of services to those new devices that might be coming 5 years from now, we will need fast data transfer, lower delays, higher reliability in our networks compared to what we have today. That is yet another reason why we constantly need to learn about wireless technology and improve it. And when it comes to non-human use devices, there is a variety of those ones that are part of this digitalization of society. So here is yet another information slide from Ericsson Mobility Report that is talking about cellular Internet of Things, or IoT, use case segments. They are categorizing this into 4 different cases. There is the massive IoT. These are small devices like smart metering or asset management that is supposed to be scattered all over our world and send small amount of data to keep track on different things. And the important characteristic here is that they should be low cost and have low energy consumption. So these can be, for example, battery-driven small devices. Then there are the broadband IoT devices that are having maybe the same kind of requirements as our smartphones. They could be drones or VR devices or fleet management, different types of things that have high throughput, low latency, large data volumes, just as our smartphones or VR glasses in the future. And then we have the critical IoT. So this might be things like connected vehicles or traffic safety of different kinds or the smart electricity grid, where we might not have that much of data that we need to deliver, but it needs to be extremely reliable, extremely low latency, high reliability and availability everywhere, so that whenever you need to send small pieces of data for something that's really mission critical, the connectivity should be there always. And finally, I was talking about Industry 4.0, so that kind of automation where we will be replacing cables with wireless connectivity in factories, for example. That is one additional kind of use case where we now have machines that are connected to the internet wirelessly or to other types of networks, and not only human-operated devices. So, to give you a brief history of wireless communications, Marconi invented the wireless telegraph in 1896, and that was sort of communication with some different characters. We could send text messages, essentially. And he was also showing in 1901 how we could use wireless connectivity to transmit data all the way over the Atlantic Ocean from Scotland to New Jersey. Then, over the last century, we have seen a lot of developments. So communication satellites were sent up in the 1960s. There were a lot of advances in wireless technology for FM radio or television in the 1950s, for example, and the mobile telephony took off in the 1980s. And then we have progressively seen how it become from analog to digital technology and how we have been starting to use it more for mobile data transfer. In the more recent decades, wireless networking, cellular technologies, mobile apps, Internet of Things, all of these things have become natural parts of our lives. So what are these cellular or mobile networks really about? Well, from the beginning, it was developed in the 1950s and 60s, at least the concepts, with the idea that we should be replacing our wired telephones with wireless telephones. These are some of the early papers on that topic. But it wasn't until 1981, essentially, where the first generation of mobile networks, or cellular networks as we're calling them, were appearing. So why do we call it cellular networks? Well, the idea is that you put out base station at a certain number of fixed locations, and user devices like mobile phones are located at different places. They are connecting to the base station that provides the largest or strongest signal, and that is then essentially dividing the world into different regions that we call cells. But mobile networks or cellular networks are sort of synonymous with each other. And in the 1980s, these were big analog phones that you can use. Essentially, people used them as car phones. And in that way, they were used in the 80s. In the 90s, they became digital phones. Then they shrink down to the size where people could actually afford them much more. So you can see here that there's like 10 years in between different technology generations. So in 2001, it was introduced, and that was when wireless internet was making its way into our phones. And with 4G, it sort of really became much more about data transfer. And now we have 5G that was introduced around 2020, and we can expect that around 2030 there will be a new generation called 6G. So today there's all these kinds of different services. We can do voice calls, of course, and texting, as we have been able to do since the 90s or 80s, but we can also use the technology for social networking, mobile apps, mobile web connections, mobile commerce. A lot of people are buying things online from mobile devices, and particularly video streaming as well. So all these kind of things of delivering things over CD or DVD or other kinds of fixed media is sort of really being replaced by wireless connectivity. So with this in mind, what is the main thing with 5G? What is happening now? Well, we can view what has happened over the past decades like this. In the past, we had different types of services that we want to deliver. Postal service, TV broadcasting, and other things that we would like to use in order to deliver communication services. And these things have, with time until today, been converging into one network, the internet, that is fitting all these services. So there's one system for everything. And how do we then connect to the internet? Well, wireless or wired connections, mostly wireless today, I would say. But you use this connectivity to do email, video, and all kinds of different things. And this was sort of viewed as, this will be the final thing, the convergence of all the things into just having one system that is sending data that can be representing any kind of service. So we don't need to build separate networks to deliver post or deliver telephone calls or other kinds of services. But that's not really enough looking into the future, because we have these different, more demanding use cases. It might be mobile broadband, it might be the massive IoT, there might be the critical IoT where we like to have really ultra-reliable communication. And if you design one network, it might not be able to satisfy their very diverse requirements at the same time. And therefore, we will in the future have one physical network that will virtualize different network behaviors depending on what kind of service that we need for the moment. And this is something that is introduced with 5G called network slicing, with the idea that the same network should be able to sort of divide its transmission resource into different slices that are then fitting for these different kind of services, and that we can on the fly create new kinds of services and slice out a certain part of our resources to deliver that. And in order to build something like that, we're also making our networks more and more software defined, so it's not what kind of hardware we put out there today that is defining how the network will be operated, but we can change this with time as new service requirements are appearing and people want to buy new services from the telecom operators. I will now talk about how the physical transmissions in wireless communication is operating, and how that is also telling us how we should design networks to make them as efficient as possible in order to deliver a lot of data, for example. So how does the physical layer operate? Well, we have this base station here, we have the mobile phone here, and it's sending a signal in between each other. And that signal is representing a certain number of bits. So here's the sequence 0, 0, 1, 0, 1, 1, 0, 1, and so on. And you see that you can't really send a sequence of bits through there. We need to represent them using electromagnetic waves, and that is what is shown here. So every time we would like to send 0, 0, we send this red wave here, and we see it repeated here. The blue wave is representing 1, 0, the purple one 1, 1, and 0, 1 is represented by the green wave here. And we are repeating those things. And of course, the color isn't there when we are transferring them. It's just a way of illustrating it here. But the main thing is that we send this wave here representing the zeros and ones. Then, when we are getting this wave received at the receiver side, we will see something more looking like this, with noise added on top of it, and attenuation, and maybe some interference from other signals. And what is the task then of communication engineers? Well, that is to develop algorithms that can look at this signal here, take samples from it, and output the original sequence of zeros and one in the end here. One question you might ask here is, why did I have 2 zeros and 1 here and not 3 or 1 for each of these segments? And also, what is the time interval for such a segment of time? And this is some of the fundamental things that are appearing. So the time interval between 2 of these transmissions is inversely proportional to the bandwidth, the spectral bandwidth that we're having measured in hertz. And then the number of zeros and ones that we can distinguish within each of these intervals, that is predicted by something called a channel capacity. And we can compute a particular value based particularly on the signal to interference and noise ratio that we are operating over. That tells you how many zeros and ones that we can be delivering. And then there are modulation and coding schemes that are actually doing this mapping here between a sequence of zeros and ones, which doesn't even need to be an integer number, and the number of different segments that we're transmitting of different shape. So this is the basic of our physical transmissions in wireless. So what are the good and bad things with wireless communication? Well, the good thing is that it's easy to deploy. We put out a transmitter and receiver, and we don't need to drag any cables between them. We can just operate anyway. And that makes it less expensive and very flexible because we can move around. But it's not perfect. So there are all kinds of issues that makes it challenging to build these kind of systems. And some of these things are political or technical that we need to overcome. And I will talk about some of these things throughout the rest of this video. So when it comes to transmitting from an antenna like this towards a receiver at a particular distance, one of the things that happens is that the signals get attenuated because they spread out over the area. And the further away you are, the weaker the signal that reaches you is going to be. And so-called line of sight, where your transmitter and receiver see each other, that is the best thing, because then the wave can transfer directly between them. They don't need to rely on anything else being around. In this case, you only have attenuation with distance because the signals are sort of spreading out. It is also possible to communicate in non-line of sight scenarios when the transmitter and the receiver do not see each other. In this case, we need to rely on that the wireless signals, the radio waves, are propagating and they are interacting with the environment in different ways in order to make their way to the receiver. So there is transmission through objects. They can penetrate a wall or a window, for example, or they can be reflections of objects when they are smooth compared to the wavelength, or scattering when they're sort of more spread out even further, but also reaching more locations. That happens when you have a rough surface, and there is also diffraction where signals can bend around corners, for example. So these are all kinds of phenomena that we are relying on in non-line of sight scenarios for the signals to make its way from the transmitter to the receiver and still being able to communicate. And in particular, in these non-line of sight scenarios, there's further challenging that are appearing. There is the thing called fading or multipath fading. So this is the thing that when the transmitter here and the receiver here are not seeing each other, so the line of sight is blocked here, the signal will make it from the transmitter to the receiver by bouncing off these different objects here. And these different objects have different total length when you are measuring the signal propagation distance like this. And that is creating different delays that turns into different shifts of the signal, and they can then add up constructively or destructively with the other copies coming from other objects like this when they are reaching the receiver. So here I'm showing a 1 meter by 1 meter distance area. And I'm showing how strong the signal is. So the maximum here is 0 decibels, and then minus 20 decibels, that is 100 times weaker than this. And you can see that in a small area like this, 1 by 1 meter, the signal strength can vary up and down very rapidly depending on small movement of you as a user. For example, if you are holding your phone. And this is then due to these different path lengths changing rapidly and interacting in a constructive, destructive manner. So that's why you can make a phone call, or you can use your device and you just move it a little bit and you get worse connectivity. So these are some of the challenges that we are having. And the fading is changing with time and frequency, for example. The next challenge is interference, because there is no boundaries in wireless. When you have a wire, you can just put it from point A to point B, and you can put another cable to somewhere else, and they will not really interfere with each other. But the wireless signals will spread out, and even if they are weak, they will interfere with other wireless transmissions that are using the same frequencies. And that makes the coexistence very important when you design the systems. And licenses of spectrum becomes important. Who are allowed to transmit, how and when. And finally, thermal noise that is appearing in our receivers is one of the limiting factors. I was talking before about the signal to interference and noise ratio that is capturing all of these things: signal strength, interference, and noise. And the noise, we can't really get rid of it. It's there because of electrons moving around in our receiver hardware, and that would be the fundamental limitation for our communication. When it comes to measuring how good a mobile network is, there are two classical metrics that can be considered: coverage and capacity. So here is a map of Sweden, and my telecom operator is showing with different colors here how good coverage it has at different locations. So here is Stockholm, for example. So these are the locations where the mobile devices can move around and still reach one of the base stations that are deployed at different locations. And you can see that in most part of the country here, there is the deep blue, but there are some places where there are weaker signals or worse coverage. So that is places where you might not be able to connect very well. The other thing is the capacity. So what is the capacity? Well, that is the capability of transferring data. So just being covered, that just means that the device can hear a base station and it can send some rudimentary signals back and forth to each other. But then, because the signals are spreading out very rapidly with distance, you might be getting different bit rates depending on where you are, and the network as a whole might also have different traffic capacity measured in terms of number of bits per second that it can deliver per square kilometer. Different services are having different requirements when it comes to coverage and capacity. So the basic things with voice calls, for example, might require 10 to 100 kilobits per second. And if you can deliver more than that to the user, you will not become happier, because it's that is how much you need in order to transfer the voice. So essentially everywhere where you have coverage, you can deliver this. And if it doesn't work anyway, so you see that you have many bars on your mobile phone, but you can't make your voice call, well, that is because you are capacity limited instead. So you are not having enough traffic capacity. When it comes to data services, higher data rate is usually always better. At least up to, say, 100 megabit per second. After a while, it sort of saturates. So if you go from 100 to 200, you as a user might not be really seeing much benefits. But up to those numbers, yeah, it will be faster in a noticeable manner. And this is generally more challenging to deliver in the networks. So you don't only need to be providing coverage, you also need to have high enough data service capability in order to make the data services work very well. So how do we build wireless networks that can deliver high traffic capacity when you're moving around? Well, one way of breaking this down is to consider a particular coverage area here. So this could, for example, be a 1 kilometer square area, and say that you would like to deliver a certain amount of traffic there, or that you would like to improve the networks from today to the future by, say, 1,000 times in this area. What could you do? Well, the basic formula is that the capacity here in bits per second per square kilometer can be divided into three different factors. The first one is the cell density. That's the number of cell or base station that you are deploying in this area. So number of cells per square kilometer. The second thing is the spectral efficiency. Bits per second hertz, or bits per these segments that I've talked about before. So I had an example with 2 bits in each segment, and it could be any number here. This is the spectral efficiency. And then we have the available frequency spectrum in hertz. So this was the number of these small segments that you have per second, for example. So you have these 3 different factors. So if you want to improve your traffic capacity, you can improve these 3 factors, and then they will multiply together. So if you target delivering 1,000 times more traffic in the future, you need, for example, 10 times more cell density or 10 times more spectral efficiency and 10 times more spectrum, and that multiplication will go up to 1,000. And there are, of course, many different ways of doing that, but these are the 3 main components that you can be working with in order to build a network that delivers more traffic capacity. So if you look a bit more deeper into this, higher cell density, well, you have our cellular or mobile networks where you divide the coverage area into these cells with different base stations, different locations, and these base stations or access points, all the users that are in the cell connect to them, and when they need data, they are getting it from that base station. And higher cell density really means deploying more base stations. So going from a situation with a certain size of the cells to making them smaller and smaller, and by densifying, you also need then more base station per square kilometer. And what are the benefits of that? Well, first of all, you have more base stations, so each cell can have a certain amount of data they can transfer. Well, then over this area, you can transfer more data. But also within the cell, when you're shrinking, the signal strength will typically be larger because you're closer to the base stations. Therefore, the signal, when it reaches you, have had less distance to travel and become attenuated. Unfortunately, this also applies to the interference that comes from the other neighboring cells. So when the cells are smaller, there will be more cells around you that might be interfering with you. But by deploying more base stations, you will be able to increase your traffic capacity if you can make sure that the amount of data that you can transfer within each cell remains roughly the same as if you had the larger cells. Then the capacity is growing with the number of cells that you're having. When it comes to the second factor, the spectral efficiency, what is that? Well, that was once again the number of zeros and ones that you can transmit in one data segment here. And I was talking before about that there is something called a channel capacity that is describing how many bits per second per hertz or bits per such symbol interval that we can transfer. The formula that Claude Shannon was computing in the 1940s is that you should take the 2 logarithm of 1 plus the signal power that you have at your receiver divided with the interference plus noise power that the receiver is observing, and this then gives you a number, which is the number of bits that you can transmit per segment. And the annoying thing with the formula like this is the logarithm. When you have a low sin-to-noise ratio, then increasing it will almost give you a linear increase in the spectral efficiency here. But once you reach, say, 2, 3, 4 bits per second in hertz here, then if you want to push it further, the logarithm will force you to exponentially increase the power of your signals in order to compensate for this logarithm. So that's really not a good way of doing it. And even if you would do it, probably interference that you get from other cells will also be increasing, because if you start increasing your power, then someone else would do the same thing to sort of try to counteract that increased interference that you caused to them. So increasing the spectral efficiency is really about other things. So it's about having many simultaneous transmissions that are directed towards the users. So if you have a base station with just one antenna that is spreading out the signal over an area, your signal will then be spread over the entire cell that this base station is covering. So therefore, only one user can be active at a time. But if you have a multitude of antennas at your base station, what we call multiple input, multiple output, or MIMO, then the base station can use those antennas to create beams that are focused in different directions based on constructive interference from these antennas. And it can focus your signal here in the local area where you are, and therefore someone being at another part of the cell can get another beam focused on its area at the same time. So you sort of narrow down the area that you are lighting up with your wireless signals. And if you then are able to serve 10 users at the same time, maybe by having a large number, like 110 at the base station, well, then you will be able to have 10 times. So more data traffic, 10 times more spectral efficiency, because every user gets the same data transfer as if they were alone in this cell. The third factor was the frequency spectrum, measured in hertz. So we would, of course, like to have more spectrum, because then we can make these intervals that we are having for every sequence of zeros and ones to become smaller and smaller. More bandwidth, they become shorter. Can we find more frequency spectrum to use for wireless communication? Well, typically the frequency bands that are useful for long-range communication is between 300 megahertz, maybe up to 5-6 gigahertz. And the further up in frequency you have, the shorter the range becomes, particularly in non-line of sight scenarios. And in that interval, we already had 2G, 3G, 4G, 5G, Wi-Fi, TV broadcasting to some extent, and military use cases, for example. So, in Sweden, for example, we have 1 gigahertz of spectrum already for cellular or mobile networks, and 500 megahertz for Wi-Fi. So, can we find more? Well, it will be hard to find things in this area where we already are communicating today. So when we were finding a few 100 megahertz for 5G in the 3 gigahertz band, we sort of start to run out of spectrum in this range. So therefore, people are looking beyond that into what we call millimeter wave frequencies, starting at around 30 gigahertz, where you can start measuring the wavelength in millimeters. So at 30 gigahertz, you have a 10 millimeter wavelength. In these higher millimeter wave bands, we typically have different propagation conditions, which are in many cases worse, but it can still work fairly well in line of sight scenarios. And designing the hardware for these new technologies is also very challenging. So even if the 5G standard is already supporting the use of millimeter wave bands, so far the deployment haven't been that much because the need for it is not large enough yet and the hardware isn't mature enough. Finally, there are some political challenges. So when it comes to different companies that are working in the area of wireless communications, they need to have a common standard so that the products that are created can interoperate. And when it comes to cellular technologies, the mobile networks, that has been relatively successful. So mobile phones, you can buy it from a variety of different vendors, and the base station equipment can also be bought from a number of different vendors. And they can interoperate very well. The standards are sort of describing the skeleton of how these devices should be able to talk to each other. But then the exact implementation details can be left to the mobile phone company or the base station manufacturer, so they can fine-tune things over time and be able to also say that our equipment is better than your equipment because we have these special features. So there we have found a good way of both collaborating in order to make sure that we have interoperability, but at the same time having the possibility of competing between companies. And also in Wi-Fi, we have the same kind of good things when it comes to standards. But so far, when it comes to Internet of Things, it's not as true. Bluetooth is there, but it's not used for all kind of things for more wide area type of Internet of Things scenarios. There are a multitude of different standards or proprietary solutions that are not really operating well together. And when it comes to spectrum, it is governments in different countries that are dictating how the different frequency spectrum can be used in their country. And they should be divided between a number of different services and different kind of use cases. And there are legacy technologies that might have been different in different countries and different decisions in the past that you need to stick with, which makes this politically complicated. But there is the International Telecommunication Union, which is a part of the United Nations, where countries are meeting and try to harmonize the use of spectrum between countries. This, for example, becomes important when building mobile phones that can be used in many different countries. Because if every country have their own specific frequencies, it might be hard to build one device that can cater for all possible countries in the world. So that's why the International Telecommunications Union are identifying certain bands and try to harmonize so that we can reduce the number of bands that a mobile phone needs to support in order to be working in all countries in the world. Finally, different frequencies might still have different restrictions on their use. So there might be a different amount of bandwidth available in different countries in different bands, and they might be assigned to operators different ways, and some of them have worse propagation conditions than others. There might be sensitive equipment that is deployed at certain locations in order to observe space or to control different kinds of systems. There were a lot of talks, for example, about interference that could be created against airports, and those type of things might say that certain frequency bands need at different places or in different countries have specific restrictions on their use and how much power we are allowed to transmit in those bands. So there is all kinds of these political challenges when it comes to building wireless networks as well. With that, I would like to thank you for watching this video all the way until the end. And if you would like to learn more about the future developments in wireless communications, particularly what researchers like me are working on today, here are 2 videos where you can learn more about that.